understood the role of visual angle and its implications for a simple magnifier or a simple microscope. Now, there was a restriction upon the simple microscope that it cannot achieve magnification beyond, let's say, 4 to 5, and that is not a mathematical restriction but more of a realistic restriction, because I lose the clarity of the image when I decrease the focal length beyond a certain point. So magnification of 4 to 5 is okay with my simple magnifier or a simple microscope. But in order to achieve a magnification greater than that, I devise a different type of microscope known as the compound microscope. I introduce two converging lenses, one known as the objective and the other known as the eyepiece. Objective sometimes is also known as the ocular. So ocular and objective are essentially the same thing. They are synonymous to each other. Objective is closer to the object, and the eyepiece is closer to the eye. And generally speaking, the objective has a focal length lesser than the eyepiece, and it also has a smaller aperture. Now let's try to understand what happens in a compound microscope. So what I'm dealing right now is compound microscope. I have an objective or ocular and an eyepiece. The objective is of a smaller aperture and smaller focal length, and the eyepiece is closer to the eye, objective is closer to the object. So this is your objective lens. This is the principal axis, and let's think of an eyepiece over here. This is eyepiece, which means you would be seeing somewhere from here. Here your eye would be situated over here. Now this guy has a small focal length. The implication of that is, let's say this is the focal length. I have kept the object over here, correct? Now, as this is beyond the focal length or beyond the focus, the rays would come like this. Just try to understand the diagram, because obviously I'm not drawing a very exact diagram. These diagrams are just a representative diagram to make you visualize the situation and to make it clear that what actually happens in a compound microscope. How do we achieve magnification? Now, this is the work of your objective. As the object is situated at a greater distance than the focus, I have a real inverted image and slightly magnified too. Now, my eye over here again has two options. Either it could be under least strain, that is normal adjustment, and under that situation what would happen is the rays would essentially be parallel, right? I'm not drawing that because that's very evident to you what I mean by normal adjustment. Normal adjustment means my eye would perceive the rays to be coming from infinity, or my eyes would be receiving parallel rays after convergence from the objective. Now, if your eye perceives parallel rays, it perceives object situated at infinity and your eye is under least strain, and that is normal adjustment, right? The other situation is if I bring my eyepiece closer to the object. Now, parallel rays is perceived when this object over here is at the focal point of the eyepiece, right? But if I bring the eyepiece closer, then this object would be ahead than the focal point or the focus. So in that situation, the simple microscope thing is going to repeat it. this would act as a simple microscope for this object, or rather the image of this object, right? And rest all things are same. Let's try to understand what exactly I mean by same. This is your ray. This is another ray. They are intersecting here. See, I'm not able to draw a perfect diagram, a perfect ray diagram, but just take it from me that essentially this is the essence of all what I'm talking about. This is the final magnified image perceived by your eye over here. And this is when your eyes are most strained. And when would it happen? When this thing over here would be capital D, where D is the least distance of distinct vision. Now, understand over here that I could have also drawn the parallel situation, but that doesn't make any sense because that's repetitive, right? I've drawn it in the simple microscope too. So just try to understand or try to visualize with that idea. Under normal adjustment, what happens? This is the different assumption. This is D assumption, or rather D situation, not assumption, situation. Now, how exactly we'll see magnification? Before this big kind of setup, my theta naught was equal to h by d, right? This is your h. Now the height of this would be h prime or h dash, and the height of this would be h double prime. Theta naught is subtended by the eye without the setup. So this is without the compound microscope. Just understand this. Now this angle is what? See, as these are paraxial rays, so this angle is equal to this angle is equal to this angle. I mean, the angle made by the horizontal with this or this or this essentially are the same. That is what I mean. Now this would be some theta prime, right? And what exactly would theta prime? Theta prime or theta dash would be equal to this h prime or h dash upon UE. What is UE? U is the value of separation of the eyepiece with this object. This essentially is your UE. And what is this thing? This is your V naught. The separation of this image with the objective. I have a complete description of a compound microscope. How essentially would we find out magnification? That is my task. This upon this, the visual angle produced by the visual angle actually I was having. So magnification or M would be equal to h dash or h prime on UE on h by d. That would give me h prime by h into now if you're careful enough, you'll understand that d by UE is similar to the case of a simple microscope. So this is the magnification produced by the simple microscope, which eyepiece is behaving like one. And this is a magnification for this convex lens, h dash upon h, which you might have read in the lens situation. And this is M1, this is M2. This is the magnification of the objective, and this is magnification of the eyepiece. And that's what's happening over here. Magnification of the compound microscope is magnification of the objective multiplied magnification of the eyepiece, and both are greater than 1, which means I can enhance my magnification without loss in clarity, and that's the advantage. Now let's try to understand it with proper formulae, because I can't just leave it like that, h dash upon h. I have to relate it with the focal lengths of objective and eyepiece. Now h dash upon h, let's concentrate on that. H dash upon h is going to give you minus V naught upon U naught. Using sign convention, V naught is in the positive direction, U naught is in the negative direction. So V naught by minus U naught, and minus comes above. What exactly is this? This is nothing but my simple V by U. That is what is happening. If I just use VU values with sign conventions, I'll get the same thing, V by U. So H dash upon H is simply V by U, right? So I can rewrite this magnification thing as, this implies my magnification is equal to V by U into D by mu UE. Now, I know from the analysis on simple microscope that D by UE would be D by FE for normal adjustment and 1 plus D by FE for the adjustment for least distance of distinct vision. So I'll have two things for magnification. Magnification is equal to V by U into D by F. This is for normal adjustment. I hope this is clear. I mean, if it's not clear, you should pause the video right over here and go through it again, because what I'm trying to tell you is slightly tricky but not that difficult. I mean, it looks difficult but is actually very easy. Now this is V by U into 1 plus D by F, and this is the case for D adjustment. I'll just write D. When I say D adjustment, what I mean is that the final image is brought to the least distance of distinct vision. Now I have further task to achieve. This V by U ratio, I still have no idea as to what would the ratio would be. For that, I'll have to use my lens formula again. Now I know that 1 by V minus 1 by U is equal to 1 by F. For your clarity, I'll just write this V as small over here. Yeah, it's a small over here. So just that thing. Now what I need is V by U. If I multiply this with V all over, I'll get just think about it, what exactly V would be. V over here is essentially related in a way. How? V by U, take this thing over here and this thing over here, you'll get 1 minus, this makes sense, V by U, it goes over here, this goes over here, V by V is 1. Now, main thing starts from here. I know that the focal length of objective is very small. Replace it with focal length of objective, or else you'll be confused all throughout. And this guy is focal length of the eyepiece. How can you forget this? This should not be forgotten, because this eyepiece is acting as your simple microscope for this magnification, right? And right now I'm bothering about V by U term, this term. Now, what you need to understand is, in this formula, V by F naught, as F naught is much smaller than my V, I can say V by F naught over here is much greater than 1. So your V by U term technically comes out to be, or rather can be approximated as minus v by f naught. Now, just try to understand what exactly is this v guy. This v guy is this thing which you're seeing v naught over here, right? The separation of the image with the convex lens. And I know that that length actually is the length of the tube. Why? Because what I do is, this is taken in such a way that the intermediate image is formed very close to the eyepiece. So if it is formed very close to the eyepiece, this UE is very small. If UE is very small, V naught is almost equal to the length of the tube. So I can say this V over here, see, V naught and V essentially are the same things. This is using the sign, this is using just a formula, and these are numbers which actually it would fit. So if I use some number over here, V naught would come over here, right? So what I can say is V is almost equal to L, length of the tube. Length of the tube or the microscope. I'll say tube because essentially microscope is tubular in nature. Put it over here. What you would get is V by U is equal to minus L by F naught, right? I'll use this thing now. If I use this thing, just write equation number 1. Using equation number 1, M turns out to be V by U minus L by F naught, minus L by F naught. This is D by Fe. This is for, I'll just say normal adjustment. What I mean normal adjustment is, the eye is perceiving the object to be at, or rather the image to be at, infinity, parallel rays. And the other situation, this thing would become minus L by F naught, and the next term is essentially 1 plus D by Fe. Fo is the focal length of objective and Fe is the focal length of the eyepiece. And this is for which situation? D adjustment. D adjustment is when the eye is perceiving the image to be formed at the least distance of distinct vision. So this is D adjustment. Now this kind of sums up the magnification of compound microscope. So what exactly happening is, it is produced by 2 steps. First is a magnification done by the objective, that is minus L by F naught in both the situations, and the second one is the magnification produced by the eyepiece, which is acting as a simple microscope. So D by Fe for normal adjustment and 1 plus D by Fe for the D adjustment. Now these two formula are to be used very carefully, considering the fact that we have made a lot of approximations over here. What approximations we have made is, first and foremost, objective's focal length is much less than this length, and the second is that this length is almost equal to the length of tube, which means that this is formed very close to the eyepiece. So these two assumptions make this formula complete, and if these assumptions don't hold, you cannot use this formula. But in almost all the questions which you will see in exam, this formula would hold definitely. But yeah, catch is, if you see that FO, FE values are very close to the length L value, this formula is not going to hold. So this pretty much sums up about your microscope, and in the next video we'll go to the astronomical telescope section.